what I plan to not to cover but to mention in this course. So this so in this we will cover we will talk mostly about the Klein-Gordon fields, where I won't speak at all about spin fields. In these lectures on the Minkowski space, we will examine the general structures, commutators, two-point functions, propagators, free field, interacting field, and the reconstruction theorem. In the third topic, we will talk about the spectral condition of quantum field theory. In the fourth topic, we will talk about KMS states, thermal field theory, and Bogoliubov transformations. Leading to the Unruh type effect. Here we will move to Kerr spacetime. So we'll discuss the general formalism and what can replace the spectral condition in this case, the various possible choices, in particular the microlocal spectral condition, and this relation to renormalization. And then we will discuss examples. Mostly I will talk about de Sitter and anti-de Sitter quantum field theories, which I know better. We will talk also about black holes and the Hawking effect. So you see, there is essentially nothing in this course concerning the perturbative approach to quantum field theory. So I suppose you have already had such kind of courses. This course can be a complement to your knowledge of perturbative quantum field theory. I won't have the time to discuss perturbative techniques in curved spacetimes. I will mostly concentrate on general structural properties of quantum field theory in the first part, and in the second part I will discuss concrete examples, mostly de Sitter and anti-de Sitter. So the mathematical level of these lectures will be wildly oscillating. For instance, today, this will be one lecture having a very deep mathematical flavor. But in other circumstances, I will not care at all about the mathematics underlying what I'm saying. So my plan for today, did you already finish to fill in the... Everyone? Thanks. So today I would like to discuss the relation between classical mechanics and quantum mechanics. Of course, this is not a new thing for any one of you. And in particular, I would like to discuss the von Neumann theorem, the Stone von Neumann uniqueness theorem, which is a theorem that is often cited, but very rarely really stated and proven. So my aim for today is to arrive to a proof of the Stone von Neumann theorem, which I tell you immediately what it is. You know the Heisenberg commutation relation can be looked at as algebraic relationships between elements of an algebra, and you want to concretely realize this commutation relations in as represented by operators in a Hilbert space. The question this theorem is asking: how many such representations? This question is one question in the general context of quantizing classical mechanics. So to answer to this question, we should elaborate a little bit about the general formulation of classical and quantum mechanics in mathematical terms. So we will arrive to a proof that there is only one representation for these commutation rules, which this theorem, of course, needs to be well stated. There are hypotheses behind this fact. And this is the departure point between classical quantum mechanics of systems having finitely many degrees of freedom and quantum field theory, which is a theory of systems having infinitely many degrees of freedom. This theorem concerning, so let me tell you the general idea, what it is the general idea before entering into the mathematical details. We have a classical system, a classical Hamiltonian system. So we can call also a classical canonical Hamiltonian systems, which is described in terms of classical variables. I will be more precise after when I enter into the details. The observables here are functions of these variables, which are points belonging to a manifold which is known as phase space. When you quantize your theory, there are two steps involved in what you call a quantization. In the first step, you promote the algebraic relationship between these variables or function of these variables. These functions, you see, if you have two observables, since they are functions, they define a commutative algebra. You can multiply your function in any order. When you quantize your theory, you replace the algebraic relationship, you replace an abelian algebra, commutative algebra, your observable, with a non-abelian one. This is the Heisenberg insight. The observables are not functions. The Poisson brackets have to be replaced by commutation relationship. I put h bar equal to 1 here. And why? Because it is impossible to precisely measure position and momentum at the same time. So in the first step, you replace an abelian algebra with a non-abelian one, which provides for you the description of the degrees of freedom, of the quantum degrees of freedom. In the second step, because you are confronted with experiments, so outcome of experiments are expectation values of such observables, you want to realize, means represent, this relationship. Here you can think of this relationship as abstract. And now you want to represent this relationship as operators in a Hilbert space. So you are confronted with the task of mapping your element of your abstract algebra, the canonical commutation relation algebra, into operators. These are operators in a Hilbert space. So in this second step, you represent your algebra, and the question arises is how many representations are there? The content of the von Neumann theorem tells you that there is only one possible representation. So the algebraic structure of quantum mechanics fixes also its Hilbert space interpretation. When you move to quantum field theory, then this kind of relationship become commutation relation between fields. Now, a field is a quantity describing infinitely many such degrees of an infinite number of such degrees of freedom. But you can still see the analogous of this relation in a relation of this form. Here you have the commutator. Suppose, for instance, you are interested in the Klein-Gordon field. Okay. This statement tells you that if you look for an anti-symmetric solution, distributional solution, then I will give a more precise content to my word. Of this equation, you have a unique solution here. The algebraic structure in quantum field theory is provided by the commutator. But when you want to realize such commutation relation by operators in a Hilbert space, again, now, since you have an infinitely many solutions, and I will show what is the technical point which do not hold in the infinite dimensional case, since you have infinitely many solutions, this problem of finding a Hilbert space representation of this commutation relation as uncountably an infinite number, but a huge infinite number, uncountably many, inequivalent solution. So this is the difference between quantum field theory and quantum mechanics. This means that if you have a Lagrangian, and if you have the equation of motion for your field, this is not enough to fix the theory. You still need to tell what is the choice you make in this representation. Since you have infinitely many distinct solutions to this equation that all have the same commutation relation. And those are inequivalent, and they have different inequivalent physical interpretation. So this is the plan of the first 2 or 3 lectures. I will enter into the detail. Of course, since here we are going to provide the examples, we even do not need to look for a proof of the von Neumann theorem in the infinite dimensional case, since I will show concrete counterexamples to this fact. So when you do quantum field theory, you are confronted with this problem. You give yourself a Lagrangian, you give yourself the commutation relation, but this does not tells you the whole story. You need to have an insight in the physical content of the theory to solve it. So this is not a complete set of information when you want to really quantize field. So are there any questions? Is there any anything which is not clear already at this level? So now we embark for the proof of the von Neumann theorem in the quantum mechanics. In doing this, I will tell you some information about the general mathematical formulation of classical Hamiltonian system and quantum mechanics. You might eventually not have yet seen. So let's think of the general structure of a classical Hamiltonian system. So as you all know, this is described in terms of canonical variables, which you can think as points belonging to a manifold, which is called the phase space, and we may assume for the time being this is compact. This is not a big if there is any mathematical word I'm using, you don't know the meaning, please ask. Not at this level, of course, but it can be that simply you don't remind. So stop me at any moment. We take this manifold as compact, and the state of the configuration of your system is described by points in this manifold, and the time evolution is also fixed by the choice of one point of points on this manifold at a certain time 0 by solving Hamilton's equation. Okay. So you can think of this state as however, idealization, which do not have counterpart in the physical experience, in that you cannot really measure with infinitely high precision position and momentum of the particles composing your system. This idealization is not an abstraction in principle. You can always imagine that refining your experimental apparatus and your experimental ability to measure better and better position and momenta of the particles entering in your system. But if you really want to describe what you do in a laboratory, you don't do this thing. So in general, if we know the position and momenta, we can measure also monomial or polynomial in position and momenta. So think, for instance, of the expression for the energy or other observables. And you can, so since we are considering a compact manifold here, so you can think of the polynomial defined on this compact manifold, or even you can close the observable and consider as observable the continuous function of your manifold with real values, but there is an enormous technical advantage in considering complex continuous functions on the phase space. So the observables of your theory are modeled as the continuous functions on the phase space with complex values. And you know that this is as the mathematical structure of being a Banach space, where the norm of an observable is the supremum for all the points belonging to your phase space of the modulus of f of x. Should I remember the definition of what a Banach space is?
I don't know what it is.
This is one example of a Banach space. A Banach space is a linear space, so it's a vector space, in which you have the notion of a norm. A norm is a function on your defined on the Banach space with values which are positive or zero eventually, satisfying the triangular inequality. Okay. So the space, and so it has to satisfy this, and second, it has to be complete. Means that if you consider sequences, Cauchy sequences in your Banach space, they converge to an element of your space itself. So the space of continuous functions defined on a compact manifold with complex value is a Banach space. So if you have a sequence such that the supremum of Fn minus Fm of x belonging to your compact manifold, this goes to 0, this means that there exists an f which is a continuous function with complex value, which is the limit of this sequence in the Banach space sense. So it is a normed complete space. This is the structure of the observables of your classical Hamiltonian system. So let's now consider what you do when you look for states. So observables are modeled as the continuous function on the phase space with complex values. It is a Banach space. As such, today is probably the most mathematical lecture I will do. So then the notion, but this is necessary to arrive to a proof of von Neumann system. A Banach space, so as such, is a vector space. You can add your observables, but it's also a Banach algebra. Means that you can multiply your observables. And also, there is an involution which sends f of x into the complex conjugate of it. And you can verify that this involution satisfies the following relationship. F star, the norm of f star f, equal to the norm of f square. This is a very important property, which is called the C star property. As such, this is an example, a very important example of a structure in mathematical structure, which is called a C star algebra. So is a vector space, is a Banach space, is an algebra, is a Banach algebra. The norm is compatible with the algebraic product. There is an involution, and this is the, up to here, you have what is called a Banach star algebra, and if this property holds, you call it a C star algebra. This is one particular model of an abelian C star algebra. Okay, means that Fg is of course equal to Gf. And the observables of a classical Hamiltonian system are organized in a mathematical structure, which is described here. We will see after that when you move to a quantum mechanical system, you also have a C star algebra describing the observables for a quantum mechanical system, but in that case, the C star algebra describing the quantum system will be non-abelian. So for a classical system, the observables, and I mean the thing you really measure in the laboratory, are an abelian C star algebra. The model for an abelian C star algebra is the continuous function on a compact manifold with complex value. I will mention or even proof the theorem of Gelfand and Naimark that tells that every abelian C star algebra is modeled like this. This is a very profound theorem, even if it's simple to be proven, that in a way changes the perspective. So you are used to first settle the geometry, discuss the geometry of your space, and then construct the observables are the function, continuous function on your phase space. The Gelfand-Naimark theorem provides to you that the opposite is equivalent. You can first tell what are the observables. So what are the things you measure in your laboratory? Settle the relationships between such observables. So construct the sister algebra of your observables. And then, using the Gelfand-Naimark theorem, you can reconstruct the geometry of your phase space. Because this representation theorem allows, once you know the algebraic relationship, to reconstruct the geometry of your phase space. So in the Gelfand-Naimark theorem, the information is that you are used to think that the geometry comes first and the algebraic relationship between the observable comes after, but you can reverse the logic. Start from the algebraic relations between the observables and reconstruct the geometry of your phase space. This is the commutative Gelfand-Naimark theorem. And this is also at the start of what is called the non-commutative geometry. When you start from an algebra of observable which is non-commutative and try to reconstruct a non-commutative manifold which is underlying. So here we have described the observables for a classical system. Now let's consider what are the states. States are essentially the outcomes are described in terms of the outcomes of your experiments. Okay, so what does a state? You have an observable. If the idealization of states are points in your phase space, what is a state? Gives you the value of your observable in that state. This is the idealized pure states in classical Hamiltonian system. Point is that you don't do this when you measure something. You know that if you want to measure a certain observable f in a state, what you do, you start repeating your measures. You make many measures, or you make replicas of your system, and then compute the average of this. And the limit is supposed to exist. This is the basis, foundational basis of experimental physics. You think that this limit exists, and this defines for you what is the state omega. This state omega as the limit when you make infinitely many measurements. Of course, a state will not be pure, but it will have a certain coarseness, which is measured by its variance. Omega is defined here. So even in classical mechanics, you are led to think in probabilistic terms because of an inherent departure from the idealization in which you can measure sharply position and momenta, and the reality of experimental physics in which you cannot. But of course, you think that in principle you could. So what is a state in the end? A state, if you look at this definition, you can extract a mathematical characterization for a state. A state is therefore a linear map from the algebra of observables, in this case, the continuous function on your phase space, into the complex numbers, but a state to be such as to be such that when you measure positive quantities, you get positive outcomes. And because of this definition also, a state has to be a linear map. This is just a description of what you do in your laboratory. Now, there is a very powerful representation theorem that completely characterizes all such maps, all such states on the algebra of continuous function. There is the Riesz-Markov representation theorem that tells you so we said that this state has to be such that f star f is to be positive or zero. And is a linear map from the algebra of observables into the complex numbers. So this generalization to the complex manifold is here, to the complex function and the complex state is question of a technical advantage. Doing real analysis is much more difficult than doing complex one. But then when we move to quantum mechanics, this will be unavoidable. We will see it in a moment. So complex linear functionals, which are positive on positive elements, and this implies that omega of 1 has to be positive. This is, you can prove as an exercise from this property. So you can, since it has to be positive, you can even assume that the functional is normalized. Omega 1 is the function from the phase space into the complex number, which is identically 1 on all the phase space. You know, since we are considering a compact manifold here, 1 belongs to the continuous function on the compact manifold. But if you think of the algebra, the sister algebra of the observables has the identity here. But if you remove the compactness hypothesis, 1 is no more an element of the algebra. So in that case, if the manifold is non-compact, we don't have the identity in the sister algebra of the observables on a non-compact phase space. This is the source of the technical advantage of considering compact phase space. So the Riesz-Markov representation theorem tells that every positive, linear positive functional on the algebra of continuous function on the phase space gamma is represented by a probability measure. This is a probability Borel measure. So it's a measure which is normalized to 1. Every functional like this, so every state is represented by a probability measure. Is there any question? I'm using words which are not familiar to some of you. Yes?
Sorry, the theorem states that you can always, that there is a representation like this?
For any linear
yes.
functional, which is positive and normalized to 1 from any linear functional omega defined on the continuous function with complex values, there exists a unique probability measure that tells you that omega f can be represented by this integral. This is one of the most important theorem in functional analysis. I don't give a proof of this, of course, but you can understand the content of it. And you can even construct a measure, knowing the values of omega. So the whole lesson we can draw from here is that even in classical mechanics, even in classical Hamiltonian mechanics, you can think in these terms. Observables are an algebra. And states have a probabilistic interpretation. In particular, pure states, which are pure states, mu of P0 of f is f of Q0 P0 is the integral of f delta of P minus P0. This is also a probability measure. Pure states are also probability measure on this algebra. And of course, pure states are such that they have no variance. If you do repeated experiments in pure states, you get always the same outcome, this one. But if you do repeated measurements in non-pure states, which are general probability measure, you get different outcomes at every step of your experimental setup. So even in classical mechanics, there is, if you really consider what you do in laboratory, you get in the end a probabilistic interpretation and an algebraic structure which is in a certain sense abstract from your experimental setup. And the first important thing is that the Gelfand-Nymap theorem tells you that knowledge of this abstract algebra allows you to reconstruct the phase space gamma. This is the first thing. And second thing, states are measured on this algebra. The states in this particular case of abelian algebra of continuous function, this is a model for every abelian algebra is representable like this. This is the content of the Gelfand-Naimark theorem. Maybe at the end of the lecture, if I have time, I will tell you how you can prove it. So states are probability measure. So this is the, let's say, general mathematical description of a classical Hamiltonian system.
Sorry, can I ask how you spell Gelfand-Naimark?
Gelfand. Naimark. Two Russian mathematicians, which Gelfand died 2 years ago, 3 years ago. He moved to Rutgers in the last part of his life. He was a mathematician, physicist, biologist, probably one of the most important mathematicians of the 20th century. I had the privilege of knowing personally Gelfand. He even wrote a letter of recommendation for me when I was looking for a place. Naimark also has studied a lot theory of sister algebras, but also the representation of the Lorentz group. Okay, so we can make abstraction from what we have learned in examining. I always lose this thing. We can make abstraction of what we have learned here in looking at classical Hamiltonian system and think in general of a mathematical description of a physical system. So on a side, you have the algebraic structure of the system. Here, we can just abandon the hypothesis that the algebra observable is the complex functions defined on phase space with complex values and continuous. This is the model we get for classical Hamiltonian system. So forget about this, but retain the algebraic structure. Simply think of it to be a sister algebra. By the way, the lecture of today is references for the lecture of today are the book Strachey, Mathematical Structures of Quantum Mechanics. Chapter 1, 2, and 3. You can find this book. In the second, Bogolyubov Logunov, Oksak, and Todorov general principles of quantum field theory. This book contains a general introduction to sister algebras applied to quantum mechanics. It is written by a physicist, so it makes the effort of not using mathematical terminology, like telling this is a quotient ring. You don't understand, but if he tells you what it is, a quotient ring, in words, you understand immediately. So here is readable from anyone having taken a course in quantum mechanics and knowing a little bit about Hilbert spaces and Banach spaces. And this is a general book. This is World Scientific. This is Kluwer, general book on the mathematical structure of quantum field theory. So these are the references I have consulted in preparing the lecture of today. So let's go. So these are the 3 chapters which are relevant for us. Not everything which is in those chapters, but the structures. You can consult this book. So the idea now is that when discussing, when facing the crisis of classical mechanics, so the idea that you can measure sharply position and momenta at the same time was analyzed by Heisenberg in his famous paper founding quantum mechanics. And even if you cannot find this relationship written in the paper of Heisenberg, you will find this rather in the papers of Weil or in the forthcoming paper of Heisenberg, but not in the first one, which is referred to as the paper founding Heisenberg's commutation relation. You have to look inside the paper to recognize this thing. This relation replacing the Poisson brackets, okay, tells you that the algebra of the observables of a quantum system cannot be an abelian algebra. You see? Do you know how this comes out of the commutation? How this commutation relation comes out of the analysis of Heisenberg microscope? So the point is that you have to look to the dispersion, let's say, of 2 observables. Suppose that these observables are 0 mean. And you know, the Heisenberg analysis tells you that, you know very well this thing. When you want to measure precisely the position of a particle, you have to use something to do it, like a photon. And the more precise you want to be in its position, the more energetic has to be the photon, because you need shorter and shorter wavelengths to do the experiments. But then, the shorter the wavelengths, the higher the momentum of the photon. So precise measurement will simply alter the momentum of the particle. So you cannot measure the momentum of the particle if you want measure sharply the position of it. So if you think that a state has to be positive, when you examine this state, the value of this thing, this is A star A, this has to be positive. You see that this is going to tell you that omega A square, look, compute this, and then minimize this expression with respect to lambda, and you derive something which is such a relation. Here you see the commutator appearing. But the analysis of Heisenberg shows that this relation cannot depend on the state. Omega is the state in which you are doing your measurements. So if it cannot depend on the state, it has to be that a commutator B is a multiple of the identity, because omega of 1, you remember, is 1. Okay? So you arrive to something which now is non-abelian. The algebra of the observables is non-abelian because of this experimental fact. Of course, this is not a theorem. This is a general idea that Heisenberg brilliantly had. Do you know why there is this high here? Alpha and I and B are self-adjoint. So the commutator cannot be. The commutator of two self-adjoint operators is anti-admission. That's why you need an I there. This is because AB minus BA, even this is a formal expression, is not Hermitian, is anti-Hermitian. And that's why you get naturally I in the commutation relation of Heisenberg. So what we retain is that we can still think in C algebraic star terms. But now you renounce to the commutativity of the algebra. You think that the algebra is non-abelian. So let me tell you once more what are the assumptions of what a C-star algebra is. And I tell you once more, it is supposed to model the observables of your physical system, either of a classical physical system. In this case, you get an abelian algebra, or a quantum physical system. In this case, you get a non-abelian C-star algebra. So first thing, A is a vector space over the complex numbers with a norm and complete. So a Banach space. Second, it is an algebra. Means that if you have two observables, A and B, the observable, which is the product of these two things, is also part of the set of observables, and the norm has to be compatible with the algebraic product. Means that the norm of AB should be less or equal than the norm of A, the norm of B, and this product is linear in each argument. So is a Banach algebra. The third hypothesis is that there is an operation star, which is an involution, means that A star is equal to A, and also A B star is B star A star. So as such is a star Banach algebra. And for the characteristic property is the C star property that tells you that the norm of A star A equal the norm of A square. This seems a mild thing, is a strong restriction on the structure. So a set which has all these properties is a C-star algebra, and as I showed you before, the observables of a classical system are a C-star algebra, and the observables of a quantum system also are organized in the form of a C-star algebra. Okay, this is the first. This is the structure that describes the observables of your system, and then you have the states. The states are the outcome of the experiments. So states are linear maps from the algebra into the complex numbers, which have to be continuous and positive. Okay? What is omega of A? Omega of A is the outcome of the observable A when you measure it in the state omega. Okay? So we have these two things, these two mathematical objects, observables, which are characterized by their algebraic properties, and states that gives you, once you give me an observable, the expectation value of the observable in such a state. Of course, there has to be, you should have enough states to separate the observables. So two observables which have the same value in all the states possible are the same observable. You cannot distinguish between them. And two states which give the same value on all the observables are the same states. You cannot distinguish between them. Okay? So I think I skip the proof of the little Gelfand-Naimark theorem. Maybe if there is interest, I will do some extra time. The Gelfand-Naimark theorem is the theorem that tells that if you have an abelian C-star algebra, you can represent it as the space of complex function of a certain Hausdorff topological space, and this Hausdorff topological space is the spectrum of the algebra. The notion, you can define the notion of the spectrum of the algebra. Let me tell you what is the spectrum of an operator. If you have an operator A belonging to a C-star algebra A, the spectrum of A is the set of complex lambda such that the operator, we are always considering algebras which have an identity inside, such that the operator lambda A1 minus A is not invertible in A. Do you understand the definition? So you have the operator A, you form this element of the algebra, and you look for another element of the algebra such that if you multiply to the left or to the right or to the left this operator, you get 1. Okay? If you cannot do this, lambda belongs to the spectrum of the operator A. It's a purely algebraic notion of spectrum. Okay? You need to invert in the algebraic sense. You look for an element of the algebra which is the inverse of such operator. So you can define a notion of spectrum of the algebra in the abelian case. This is the spectrum of the operator. You can define the notion of spectrum of the algebra. These are the multiplicative linear functional of the algebra. This is the so-called Gelfand spectrum of the algebra. And so what the theorem of Gelfand says, it says that if you have an abelian star algebra, C star algebra, think unital. If you have a unital abelian C star algebra, this is isometrically isomorphic to the space of continuous function from the spectrum of the algebra into the complex. So you have identification between this object and this concrete algebra of functions, and here you have reconstructed this is a Hausdorff topological space, which you can think of it as your phase space.
You define the sigma of A to be the collection of spectrums of all operators?
No, let me tell you what it is. So the collection of characters on the algebra means functionals from the algebra of the complex which are multiplicative. So they are linear. This is because the algebra is abelian. And they are multiplicative. This is the Gelfand spectrum of the algebra. Functionals, all the functionals which satisfy these things define the spectrum of the algebra. Why they define the spectrum of the algebra? Because if given A belonging to A, if lambda belongs to the spectrum of A, lambda belongs to the spectrum of A, if and only if there exists M belonging to sigma A such that M of A equal lambda. That's why you call it the spectrum of the algebra. So you can study the topology of this object, consider the continuous function on this manifold with complex values, and this is identical with your original algebra. This theorem allows you to reconstruct the phase space knowing the algebra of function of it. So the geometry of the phase space is encoded in the algebraic relationships between the observables. This is commutative geometry. Yes?
Sorry, you said the Hausdorff space was the spectrum or the algebra?
Excuse me?
You said the Hausdorff space was the spectrum or the algebra?
Sigma is the... You can give a topology to this object, which is the weak star topology. So these are really mathematical notions of functional analysis, which I don't want to enter in here. But there is a way to give a topology to this space, And once you give this topology, you identify this space and the original algebra from which you have started. This is the little Gelfand-Naimark theorem. Why little? Because it speaks about a billion sister algebra. There is a big Gelfand-Naimark theorem that provides the same characterization for any sister algebra. Any sister algebra, because of the Gelfand-Naimark theorem, is a closed subalgebra of the space of bounded operator on a Hilbert space. So you have a model also for non-abelian sister algebra. So in conclusion, you have, in the abelian case, the continuous function on a Hausdorff manifold with complex values. In the non-abelian case, the subalgebras of the bounded operators on a Hilbert space. This is supposed to describe classical dynamical system. This is supposed to describe quantum dynamical system. Here you can reconstruct the classical geometry. This is the starting point from non-commutative geometry. Other questions?
When I have like a matrix and I ask like what's its spectral decomposition, I write down the eigenvalues and construct the sum, right?
This is in Hilbert space, you mean?
Yeah. So how do I reconcile that?
This is once you represent this is the next step we are going to take, how to represent this algebra in a Hilbert space.
Okay.
Can you repeat what you mean by the double arrows here? The relation between the spectrum of the algebra and the spectrum of the operator?
Means that if lambda is a point in the spectrum of a given operator of the algebra, this is true if and only if there exists a linear multiplicative functional on the algebra satisfying this property such that m of a, so this is a number, equal to lambda. You can do this only if there is an operator such that lambda is in its spectrum, and vice versa. If lambda is in the spectrum of an operator of your algebra, there exists such a functional. You can construct it. It's not difficult. The point is that I don't have the time to explain it. It is really simple. So if you look at this book, the proof is half a page. Okay. So we can discuss it maybe at the end if there is some time, but I don't anticipate I will have time. So this is, but the point is exactly this. We are distinguishing the algebraic part of the properties from the concrete realization of such algebraic properties in a Hilbert space. This is precisely the main idea of all these things. It is useful to separate these things because in the end, in quantum mechanics, this will be the same thing. If you give yourself the algebra, you also have one and only one Hilbert space representation. So one and only one spectrum. But if you do quantum field theory, if you give yourself the algebraic properties, you have infinitely many possibilities. So infinitely many possible spectra also, you see. So this is the lesson you understand when you separate the thing. The algebraic structure is distinct from the Hilbert space realization of such algebraic structures. So the second, the thing we are coming to discuss now is precisely this. This is one of the most, by the way, these things stems out from quantum mechanics, but it is at the root of, let's say, a considerable portion of the mathematics of the last century and the present century. Many developments in mathematics come out of this. For instance, non-commutative geometry comes out of this. We are not just discussing formalism, but we are entering in the deep earth of the subject. So we do have a sister algebra once more, is a Banach algebra. It's a Banach space. There is a star operation. And this is the characteristic property distinguishing Banach algebra from C-star algebra. And we have a state. A state is a positive, normalized function. We always assume that there is a unity in the algebra. I don't say it anymore, but my hypothesis is always understood that there is the unity in the algebra. And okay, so what is the, once more, what are states? States are your outcomes are described by the outcomes of experiments. So you have your observables, let's say position, let's say momentum. You measure it in a state of your system. The outcome is omega of the observable. Yeah, the numbers you measure. And they depend on the state you use. There are different states, so you get different outcomes of your measurement in the same way as if you look to your system occupying position Q and P. This is always your system, but it occupies position Q prime and P prime. So the observable is the same, the state is different. Is it clear? So the point is, to come to the question is there an Hilbert space realization of this thing? So we have to introduce the notion of representation. Of the algebra. At the moment, the algebra is abstract, is a structure in itself. Now we want to embed or to map the algebra in a subalgebra of the bounded operators in a certain Hilbert space. So concretely realize the algebra in a Hilbert space. How could we do this? So let's say a few words about the names. A star homomorphism between an algebra A and an algebra B is a map P from A into B that respects the algebraic structures. This means P of A plus B, these are elements, let's say P of A1 plus A2 equal PA1 plus PA2. PA1, A2, these are elements of the first algebra. P of A is an element of the second algebra equal P of A1, P of A2. So the algebraic structure is respected. P of A star equal P of A star. And also P of 1A equal 1 in B. Okay? It is not difficult to show that if you have a star homomorphism between algebras, the norm of P of A in B is less or equal than the norm of A in A. Yes?
Sorry, doesn't the multiplicative property imply the unit thing that you put there?
Not really. It is not completely you think you put 1 here? See, yes, probably, yes, yes. Okay, this is a consequence of this. Okay, so you have a star homomorphism imply this. This is the proof of this formula is based on an important formula which is called the spectral radius. And you see here why the C star property is strong. So here we have defined the spectrum. We have the following formula. R, the spectral radius, is the supremum of the modulus of lambda. Lambda belonging to the spectrum of the operator. This is equal to A to the n to the 1 over n limit. And this is less or equal than A, the norm of A. So this formula in particular implies, so the only thing that needs to be proven here is that this sequence has a limit. Okay. It is standard. It is similar to what you do in the Hilbert space case. So the point is that you have an identity here when A is a normal operator, and the normal operator is an operator which commutes with the star operator. If A is a normal operator, R equal to the norm of A. You get an equality here in the case of a normal operator. I don't have the time to enter in the details of the proof of this, but in the book I quoted there is the detailed proof of all these statements. And this in particular implies also this bound. Okay. So now I can state and prove one fundamental structural result, which is at the basis of the proof of the von Neumann theorem, which was the aim of the lecture of today, but maybe we'll prove it as the first thing in the next lectures. So this is, let's say, this is one of the most important theorems. I've lost once more the eraser. So a representation is a star homomorphism of the algebra into the bounded operators in a certain Hilbert space. This is what a representation is. It's a map which preserves all the algebraic structures and is realized as a subalgebra of this particular subalgebra. The bounded operators in a Hilbert space is another fundamental example. It's the second and last fundamental example of what a C-star algebra is. So we have the model for the abelian case. This is the model for the non-abelian case. And then we have this fundamental theorem, which is called the GNS representation theorem. Give yourself a C-star algebra A and a state omega. There exists a Hilbert space H with a cyclic vector psi omega I will tell you what the meaning of the word cyclic is at the end. And the representation of the algebra such that omega of A equal the expectation value of the operator pi of A in the state omega. And every other representation, if you have a second representation with a cyclic vector, so let's call this pi omega. If you have a second representation, pi, in a Hilbert space H with cyclic vector psi, if you have a second representation such that omega A equal psi P of A psi, then these two representations are unitarily equivalent. They are the same representation. So, if you give yourself a state, you have a Hilbert space interpretation of the state. In terms of a cyclic vector in a Hilbert space is a vector such that if you apply all the operators you construct and you close linear combination of such elements, this is the whole Hilbert space. Okay? So knowing the operation of all the elements of the algebra on the cyclic vectors means knowing all the Hilbert space. There is nothing left out. Okay? So this is the GNS representation. It provides a concrete map between the abstract algebra of observation of observables and a Hilbert space representation of it. So also in this case, if you think of the Dirac axioms for quantum mechanics, these are a purely algebraic interpretation of these axioms. Yes.
Sorry, when you wrote H sub omega, you mean, does omega represent a single state or the space of all states?
H is the Hilbert space associated to omega.
So,
I will go to construct it. I will tell you.
But it corresponds to a single state.
Omega is one state. But what does it mean, a state? It means that is a map from the algebra to the complex numbers. It means that if you have an observable, you know what is the expectation value of the observable in the state omega. If you have a second observable, you know also this. And you know these numbers for all the elements of the algebra. The point is that such numbers can be interpreted as mean values of operator in a Hilbert space into this particular state, which is cyclic, the cyclic GNS vacuum, we can call it like this, associated to the state omega. Okay.
You always get a separable from the space?
Here we are always assuming separability, yes. Because we assume that the states, the algebra, everything here is separable. Topologies. Okay, let me tell you how you do this. This is also, let's say, this theorem is also at the basis of the problem you face when you want to quantize the field in a curved space-time. You have an algebra. The algebra is uniquely fixed by the commutation relations. So the algebra is unique. And then you have your states. This is also true by the way, in Minkowski space, because you can have the vacuum, or you can have the KMS states, and those are inequivalent. There is no unitary map between those two states. They give inequivalent outcomes they describe in equivalent physics. So this is the mathematical way to approach the problem, also in the case in which not all the representations are equivalent. Here, this is true. This is true in general. Here, if you give yourself an algebra, a sister algebra, and you give yourself two states, for sure you are constructing two inequivalent representations. The content of the Stone-von Neumann theorem is that if you give yourself the Heisenberg algebra, so the algebra of the commutation relation, all the irreducible representation of the Heisenberg commutation relation are equivalent. Once we have stated and proven the GNS construction, then the proof of the von Neumann theorem will be more or less evident. So the first thing is to set up a Hilbert space, construct a Hilbert space. What do we have? We have an algebra, A, and we have a state on A which is positive. Means of A star A is greater or equal than 0. But there are elements in the algebra such that omega of A star A is 0. In principle, there is such a subspace. This is indeed so J, the elements of the algebra such that omega of B star A is 0 for every B in the algebra. This is equivalent to this because of the Schwartz inequality, is an ideal. Okay, means if A belongs to J, also multiplication of A by any element of the algebra to the left also belong to J. Such structure is called an ideal. Okay. So if we define a pre-Hilbert space being the algebra itself, when we input the scalar product defined this way, this scalar product is positive semi-definite. So we have to quotient the ideal of the null elements. So we can write this quotient, the ideal as such is a subspace. So this is also a vector space. And when you consider the scalar product on equivalent classes, this is now well-defined and positive. So we have constructed a Hilbert space this way. The Hilbert space is constructed on the algebra itself, quotiented by the ideal of the elements having 0 norm. Okay. Now we have to define so the state gives the Hilbert product on the algebra itself, but we have to quotient using the standard techniques of completion. We get a pre-Hilbert space, and then we complete, and we get a Hilbert space. How do we define now the representation phi of A of an element of the algebra on the Hilbert space, state B? This denotes an element of the Hilbert space. we define this in the obvious way. It's the equivalence class of AB. This definition is well posed because the ideal is a left ideal. Okay. So this is more or less obvious. If you have already seen how do you complete a Hilbert space, we are using standard techniques for getting a Hilbert space from a pre-Hilbert space. And this definition you can check because the ideal is a left ideal, respects the algebraic structure. The only thing that needs to be checked is this one. This is the only thing that needs to be checked. It is a star homomorphism because up to here we don't know. We have a map, but we are not sure that we respect the norms. So if we now compute this thing, we get. I've written here the details. So let's compute the norm of PA applied to B square. This is the norm, according to this definition, of AB square. Okay. And this is what? This is omega B star A star A B, according to the definition. So the point here, there is a small technical passage that consists in defining an auxiliary state, omega B of C equal to omega B star CB. This is also a positive linear functional on the algebra, and as such, it satisfies the okay. Since it is a little bit late, I'll don't do the whole steps, but it's really elementary. Then, if you think of this property and you input this here, you get that this is positive. This is less or equal than A square B square. So this is a technical step in which you verify that you have really defined a star homomorphism between the algebra, the abstract algebra, and the operator in this Hilbert space. So in the end, so this satisfies this construction. You can check it, and if you take the book I told you, the details are inside. You can check this step, and the final important thing is what it is. What is the cyclic state? The cyclic state is just the equivalence class of the identity in the algebra. So you can see here, when you apply the representation of an elemental of the algebra on the cyclic state, you get the equivalence class of A. So you get the whole algebra represented. So this is the construction of the GNS representation. It remains to be proven the uniqueness of this representation. So if you have a second representation with a cyclic vector, you simply define U1 minus 1 of the representation you have just constructed applied to. This is a definition of an operator. This is the second representation in the second cyclic vector. So you can verify that this map is unitary, and because of the cyclicity of this object, this is a dense set. So you can identify U minus 1 P omega of A. This is the map. This is the definition of the map. U with P of A.
The right-hand side is filled to a second state.
This is you have a second representation.
Yeah.
And the second cyclic state, another Hilbert space. This is a map from the Hilbert space you have already constructed, H of omega, into the Hilbert space H. You are supposing that it exists. You define this map. You see that this map is an isometry. I mean, the second Hilbert space also satisfies the same relationship. Psi, P of A psi. This is omega of A, which is also psi omega, P omega of A, psi omega. This is the key point. They do have the same expectation values. So these operators, because they do have the same expectation value, is unitary, and because these two vacua are cyclic, this is an identification on a dense set, because this is the vacuum. You apply the Wool algebra on the vacuum. You are defining this operator on a dense set of your Hilbert space, and therefore you get that U psi is mapped into psi 0, and the representation is unitary equivalent to the GNS representation you are constructed this way. I mean, here, what is the logic? We construct one representation. This is concrete. It's extremely simple. You define a Hilbert product, and you define a representation. You check that this representation, because the cyclic vector is 1, when you do psi omega pi omega of A psi omega, what is this? This is A. This is 1. This is omega of 1 star A. This is omega A. So we have constructed a representation having the required property of being the expectation values in this vector of the operator representing A equal to the expectation value of the state of the operator in the same state. Now, we suppose that there exists a second representation. We don't know how it has been constructed, but it exists with a cyclic vector and also satisfying the same property. We show that this map, defined this way, is unitary and intertwines the two representations. So the proof of the GNS construction is really simple. The only thing that really need to be checked is this one. The rest is more or less. You give yourself a state, you have a Hilbert space. A state, a Hilbert space. And if you have a second Hilbert space in which you have the same identification between mean values and the values of the state, it is the same. So it is unique. The map between states and Hilbert space is unique. So because of this unicity, we can prove the Stone-von Neumann theorem. Uniqueness of the Stone-von Neumann theorems comes from the fact, let me tell you the beginning of the story, and then the proof I will give you at the beginning of next lecture. Now we get into a concrete algebra. So we have the Heisenberg algebra. Of course, this is not a very good way of writing it, because this cannot be bounded operators. This is very well known. It is immediately from here that you can't, this cannot be matrices, finite dimensional matrices, because if you compute the trace of this, the trace of the first left-hand side is 0, and the trace of the right-hand side is just the dimension of the space. So cannot be matrices that realize this commutation relation. Cannot be bounded operators in the Hilbert space. If you compute P commutator Q to the n, this is I minus I guess, Qn minus 1. So if you compute the norms here, you get that n norm of Qn minus 1 is less or equal than 2 norm of P norm of Q to the n. So if you do this, you see that norm of P norm of Q has to be greater or equal of n over 2 for any n. So they cannot be both bounded, this operator. So we are outside of the formalism. This is not a C-star algebra. So the trick of Weil was to consider bounded functions of this operator. Okay. This is also physically reasonable, because you never can measure a position that goes to infinity. You never can measure momenta that go to infinity. You always can measure bounded functions of position and moment. You can measure the position of the object in your laboratory, which have finite velocity. So Weil proposed to use bounded functions of position and momenta, and you can check. We will do it maybe at the beginning of the next lecture, that the Heisenberg commutation relation can be rewritten this way. Then you can see that you can provide a norm on this algebra close with respect to the norm and get a C-star algebra, which is the Weil C-star algebra, which describes one or n free quantum particles. This is the algebra of the observables of one quantum particle, non-commutative. So you want to construct, so this is just an algebra. Now the question is, how do we construct representation of this algebra? How many representation? How many inequivalent representation of this algebra are there? The answer is there is only one representation, one irreducible, strongly continuous representation. So this is the proof of the theorem is now extremely simple, because what we are going to do, we are going to prescribe a functional omega. We construct first the operator W alpha beta, which is a to the eq alpha plus EP beta, okay, which is written in terms of this very simply. We will do it precisely on Monday. And then we prescribe the value. So we give a functional on such algebraic elements, which is this functional. The expectation value of such object is this. Okay? Once you do this, you can go through the GNS construction and construct the representation. And you see that because there is a projection operator in the algebra that you can easily construct, this object P, 1 over 2 pi, integral, this function, e to the minus a squared plus b squared over 4, w of alpha beta, integrated over the alpha d beta, and here the hypothesis of continuity enters. And this is the hypothesis that fails in the infinite dimensional case. This object is a projector, p squared equal p. So there is an eigenstate of this projector in the Hilbert space, which is the Fock vacuum. And because of the uniqueness part of the GNS construction, all other representation, they do have this vacua, which are also obtained by applying the projector operators, and they have all the same expectation values, so they are all equivalent. We will redo this at the beginning of the next lecture, and then we will move to quantum field theory.
So it depends on the choice. Still depends on the choice of omega.
But the point is that whatever your choice, you always have this, because there is a projector. Because this I will prove now. I mean, all the elements of the proof are there. Since this is a projector, I mean, this is algebraic. Is in a way algebraic. Give yourself this w alpha beta, make this integral. You can do it. Because this is a unitary operator, this function is integrable. You can give a sense to this integral. And you can show that this is a projector. So this is represented in any representation. So when you apply this projector in your representation, since a projector has eigenvalue 1, there is a particular vector in your representation, and the expectation value of W on this vector in any representation is precisely this number. So because of the GNS construction, they are all equivalent. Yes?
I'm sorry, what exactly are alpha and beta in this scenario?
Are numbers, real numbers. And you will see, we will do it again on Monday, and then you will see appearing here the symplectic vector space of classical mechanics. When you make product of these objects in between themselves, the phase is just a symplectic form of classical mechanics. So this will be the starting point of the next lecture. Questions?
Is there a way to extend this formalism for the non-compact case, or it's, I mean, do you prefer the compact space always, and you always use this trick for compactifying your space because that's just, you know, torus in some sense? That's, you project your.
I mean, this kind of theorems has a very long output in group theory, of course. There's the Mackey, starting from Mackey onwards, there are zillions of modifications of this theorem. There is a wood branch mathematics standing out from here. But the point which interests me is that you can't do this. Even if you can do this in the infinite dimensional case, the hypothesis we are using in the finite dimensional case fail to apply in the infinite dimensional case. This is the point for interesting us. But if you want to know what are the generalization of this theorem to other groups, not to representing just R3, but to...
So the point was not to, I thought the point was to view W as a plane wave generating your whole functional space, L2 space on
This is W is generating the algebra. All the elements of the algebra can be obtained as these are operators in the algebra. Q is an element of the algebra. So we are generating the algebra using this thing. This is a representation of this commutation relation. Nothing else.
So we are in a non-compact case.
So I'm thinking about this compactification, I think, here.
Yeah.
So those are just plane waves that generate your whole functional space.
We are representing R3 indeed. The Heisenberg group is a copy of R3. But we can do it for this theorem has an enormous family of generalization, and there is a paper on the internet you can consult by Rosenberg telling the history of the Stone-von Neumann theorems as well as generalization to other groups and other contexts of mathematics. So this is really the starting point of many generalization of mathematics. Here, passing to this form, to this exponential form, is just to get bounded operators. The question is not that you have a circle here. As he says, this is not an integer number. This is an operator. This is, by the way, this is a formal way of writing. What you have to look is just, I mean, the veil algebra is defined here. Forget about this because these operators do not exist at the moment. They will exist as an application of the Stone theorem. This is the representation, the algebra of which we are looking, the representation of which we are looking for. Okay. We will redo this at the beginning of next lecture and then go.